G'day everyone, here's another video for today, still the 31st of March. I've done about 5 or 6 videos today and about the same yesterday, so lots and lots of fresh work up there across specialist methods and apps. This one's for methods and this is area under the curve. So we've done integration. We've got that idea that we can integrate a function. We can also differentiate a function giving the gradient function. If we integrate that gradient function, we get back to the original one, remember, plus c on the end. If we're given a bit of information, then that means that we can add that in and find the actual graph, not just the family of graphs. Have a check back on the previous one if you need to on there. So, area under the curve, what are we doing here? Well, here we go, we've got an equation. This is nothing fancy, this is nothing fancy at all. But this here is this red graph. Now from that red graph, what we want to do is we want to figure out what is the area under here. What's the area under here? Well, we could do a couple of things. Now the first thing I could do is see that and say, well, let me break that up into rectangles. I know the formula for a rectangle, that's pretty easy. And I can start fitting some rectangles in here. Okay, so let's take just this area here and I've expanded this guy out. Okay, notice I've got here the value of 1. Okay, so here's 3, so I'm only getting up to about there. So I've expanded this out, and what I've done is I've divided that section up into 5 rectangles. You might only see 4, there's 5 of them there, into 5 rectangles. Now, here is the first rectangle, right? It has a height of 0. So 0 is the height there, then 1 rectangle there, there, and there. There's actually 5 rectangles. Now what I'm actually doing in this one is on what we're calling inscribing the rectangles. Notice how the rectangles sit inside of the line? So I'm inscribing the rectangles. I could do the opposite and do it on the other side and then follow the green pen. The first rectangle would actually be that one there. The second rectangle would be that one there. Third rectangle there. Fourth rectangle. And then the fifth rectangle would be that one there. So they'd hang on the outside of the line, of the curve. So that would mean that my answer to doing the ones on the outside would be larger than the real value I want, and the ones on the inside would be smaller than the value I want. Okay? We'll come back to that in a minute. I'll show you more about that. Have a look here. Area equals. This is saying the sum of this equation between A and B. Now A and B, A would be right here at 0 and B would be right here at 1. So this would be between 0 and 1. Now what's this telling us? This is the value of the function times the small change or the small difference. This guy here, that is the thing that I'm working with. That's the size of each rectangle that I'm doing. So that's really the value of the function times by the base. That's height by width. That will give me the area of one of these rectangles. And then when I combine that with summing them all up between A and B, that's going to give me the area under the curve, or outside of the curve if you like, for this particular part. And I could apply that to the whole thing if I wanted to. Now how would we do that? Well, here's the first rectangle. That's the one that's 0 high by 0.2 wide. This next one would be this height right here, multiplied by 0.2. The next one would be this height right here, multiplied by 0.2, plus, work it out. Too much work, I don't want to do that. But that's the theory, and we could do that. We could do that, we could work it out, and we'd get an estimate for the area under the curve. Now if I did, this is where I'm coming back to what I said before, if I did do the ones here inside the curve, and then I redid that estimate for the ones outside of the curve, well I could average those two values, and that would get me pretty close. That would get me pretty close. But here, think about this. I'm going to exaggerate this curve, okay? If I had a curve that was doing this, see how it's quite a steep curve? Well, let's just pick a rectangle and I'll exaggerate with a really big rectangle. Okay? See how I'm touching that point there? Okay? Yet if I did the other one, it would be... Right, now have a look for me. Have a look for me at the relative area of this space here with the relative area of this space here. So this area versus this area. Can you see how they're not equal? And that's not surprising because it's a curve. But that means that doing this for the overestimate and doing it for the underestimate and averaging it is never really going to work out that well because we're on a curve. If we were on a straight line between those 2 points, it would split it exactly in the middle. But we're on a curve, so it's never going to be right. Now you might say, well, across the whole range of it, it'll all balance out, and it might, but if I'm only working out across a small area, it might not. And I don't know whether I'm accurate or not. So this system is okay, but it's not great. It's not great. Now before we get into this mathematics, what we could do here instead is actually use a trapezoidal rule. Now a trapezoid is this sort of shape, right? A trapezium. So can you see how a trapezium, if I fitted them in here, they'd be a lot closer to that line, okay? So a trapezoidal estimate may well do better. But they're a little more difficult to work out because I've got to do this one plus this one, divide by 2, multiplied by this one in that calculation part. And look, I already think this is too much work, so this is even going to be more. So I'm probably not going to be doing it, but it's a good little idea to do. Now a third way that we can do it, before we even get on to the exact, is Simpsons Rule. Now, when you look at Simpsons Rule, what we're doing there is we're not trying to fit a rectangle, we're not trying to fit a trapezium, we're actually fitting a curve between the 2 points. So on here, we would, in this range here, be trying to fit a curve between there and there that would neatly pick that up. There's a bit of work in that, bit of series work. Have a look into this. It's good to look into outside the course, but good to see and good to know about. Also, it builds into your series work of understanding how a lot of these things work. So, good to look into outside the course. Let's get on to this. This is where we really want to be, right here. Because once we know this is the theory, this is what we're doing under this curve, we can transfer this into this. Now, what are we doing? We're doing the limit. Remember back to differentiation things? The limit as the small change in x gets to 0. So as we reduce down this value, and by reducing that down, I'm putting more rectangles or more trapeziums into this space. Theoretically, that reduces the error that would happen here. So because that reduces that error, it means that my estimate is going to be a lot closer. Now remember, the theory is as this tends towards 0, never gets there, as it tends towards 0. Between some lower limit, in my example here that would be there, some upper limit, that would be there, of this guy, which is exactly that. So I'm really just adding on the fact that this guy is getting smaller and smaller. Now that, if you do that, what you find is that's the same as integrating that function between a and b. So if you integrate a function between a and b, and I'll show you how to do that in a minute, then what you're going to find is that is the closest answer we can get because we're doing as the limit approaches 0, as the small change in x approaches 0. Now another way that that's often written is like this. We can say this one. We can say that the integral between a and b of f dash, important, of x dx, so we're integrating the derivative of x. Now you would, forget this part here, you would just say, oh, well that's going to be f of x plus c, right? Integrate, add your value. Yes. Now this is where the next part, I haven't done this yet. We throw these limits in and actually that's going to be equal to the value of f of b minus the value of f of a, because the c part cancels out. Let's do an example here. Hopefully you've got all that. Rewind the video if you need to. Let's do an example of integrating. Why don't we use this guy? I'll get rid of over here. All right, let's get rid of this. And let's do an integral on this guy. So, to make it a little easier, I might just multiply that out. I don't think I need to, but let's do that. Let's go f of x, I'll change from y. Wouldn't that be equal to x squared minus 6x plus 9 plus 5? So we'd end up with x squared takes 6x plus 14. Double check me on that, hopefully I'm good there. Right, let's use this guy here. First of all, let's just use this part. Okay, that's the important part for now. So if I'm going to integrate f of x dx, integrate f of x with respect to x, then that says I've got to integrate this, right? So this is the integral of x squared minus 6x plus 14. So that then means that I'm going to end up with x cubed over 3 minus 6x squared over 2, so that'll be 3x squared, plus 14x. Now, if I was just doing a regular integration, I'd want to put plus c on the end here. And for the moment, I'm going to. Now, you're going to see that that doesn't actually matter. All right? Because now I'm going to go back to my question and I'm going to build in a few things. Okay, I'm going to build in 0 and 6, because that's the area that I want to find here. So I'm going to build in 0 and 6. So I'd have 0 and 6 there, 0 and 6 there. Now once we've done the integration, which we have here, we now no longer have f of x. We're actually working out the area or the integral. Now there's a difference between the two. For the moment, I'm just going to use them interchangeably, right? But there is a difference. They're not the same. So I'm just going to now call it area, because that's what I would be working out. I'm working out the space in here. So now what I do, instead of putting the limits here, that's the lower and the upper limit, I make a square bracket and I put the 6 and the 0 over there. So that tells me I've done the integration. Now I just have to substitute my limits. We always substitute the upper limit, then the lower limit. So this would become, x cubed. So that's going to be 6 cubed over 3 minus 3 lots of 6 squared plus 14 lots of 6 plus c. So that's my upper limit. Then what I'm going to do is go minus, I'll put a bracket for the moment, my lower limit. Now, choosing 0 was really good because this makes it easy, right? So 0 over 3 is going to be 0 minus 0 plus 0. Now, here's the key thing, plus c. Now, those among you that are a little ahead of me will see that I've got a plus c here and I've got a minus c coming out here. So those two things are actually going to cancel. And that's why here I don't need to worry about the plus c. Because when I put it into the upper limit, I'm going to end up with a plus c. When I put it into the lower limit, I'm going to end up with a minus c. And the two will cancel out. So I don't need to worry about c. This is why this formula is like this, rather than having a plus c anywhere in there. So this formula is absolutely fine as it is. Okay? Right, now I just need to tidy up this top line, or this top part of it. I'll come over here. Let me come over here, a bit of space. 6 cubed. 6 sixes are 36, 216. There we go. 216. Now, 216 divided by 3 is going to work. It is going to work because those numbers add up to 9, which is divisible by 3. We get back there in a minute. 36 times 3, 90, 108. Minus 108. 14 by 6. 10 by 6 is 60. 4 by 6 is 24. 60, add 24, 84. It's plus. And the C part's all gone. Nothing in here. So then it's just a matter of number crunching. This one, what do we got? 210 is going to be 70, that's going to be 72, minus 108 plus 84. These two are going to make 156, minus 100 is going to be 56, minus another 8 is going to be 48. Right, there's my answer. Now, what does that 48 mean? Well, if this graph was in centimetres, so this is 6 centimetres, this is 5 centimetres, then the area in there would be equal to 48. Now I've got a little bit of a problem with that. I'm going to double check my numbers, because if I just went 6 by 5, that only gets me 30, and clearly this has got to be less than 30. So I think I might have a mistake somewhere. Let's double check. This is going to be x cubed over 3. That's 6x squared over 2, so that's okay. 14x. Okay, maybe I made a mistake here. What do we got? X squared minus 6x plus 9 plus 5. I like that. You might have already spotted my mistake. 6 cubed, 36, 36, 180. Yeah, no, 216, I'm happy there. 36 times 3, 90, 108, I'm good there. 60, add 24 is 84. No, I'm good there. What do we got? Oh boy, I don't know where my mistake is. I'm sure I have made one. You'll get the idea of it. Let's see. 72, that's correct. Minus 108. What do we got? 156, 56, 48. Okay, I don't know where my mistake is. Put it in the comments below. Tell me where I made a mistake. The concept is fine. So this in this question would be, let's say, centimetres squared. But I've got an issue with that because it doesn't look like I've got that amount of space here. I don't think I've done something wrong, but maybe I have. I'm not really sure. That's all right. I'll try and figure out my mistake here. I'll do a couple of examples of this sort of one. But the key idea is to remember this sort of idea. This is the outcome of the whole thing. But notice this is working from the derivative, so a little bit different here in a way. The what I did before shows you the process all the way through to get to, well, a wrong answer. I think. I'll double check it. That's all right. I can't see where I've made a mistake. Anyway, email me, chris.simpson@siwa.edu.au, or put it in the comments and tell me what I made a mistake on, because I'm not so sure. Anyway, enjoy this one. Catch you later, guys. See ya.